Let's talk about finite state machines. So finite state machines are not actual physical devices like you might think they are. When you call something a machine, you think of something that you can see, something that does something, and it's present physically. But a finite state machine, which can also be called an FSM, is not an actual physical device, but actually more of just an abstract model. Now, those models are often used in order to explain behavior of actual physical devices, devices that have some type of computing component. But the FSM itself is only a concept and not a physical device. Now, right now, you might be not understanding how we can have some kind of model that will describe the behavior of some physical devices, but you'll see soon enough how we do this and how this is done. Here are some examples of some physical devices that we can actually use FSMs to describe when we're trying to describe the behavior of these devices. A turnstile, and that's one of the examples we're going to use. A gumball machine, and we're going to use that example too. A combination lock is another physical device that can be described by using this abstract model, an abstract model called a finite state machine. And then also just the computation involved in password verification. If you start up a computer and you need to type in a password, or maybe you log into a website and you need to type in a password, that part of the computation process where you're trying to where the password needs to be verified, that's another procedure that can be where we can use a FSM to describe it. So if a finite state machine is not a physical device, then what would we say it is? What makes up a finite state machine? Well, here is what makes one up. You have to have these different things here. A finite state machine has to have a set of states, and when I say states, that's within the context of states like off and on. This machine is either on or off, or maybe something is locked or unlocked, or something like that. So that's the kind of states we're talking about here. It's going to have a set of states, and you'll see some examples. So right now it might not make a whole lot of sense, but a set of states, a current state, a set of possible inputs. We're going to be able to do something to this machine in order for different things to happen. But then we also have a set of rules in order to determine what happens based upon the different things that we input. Now, some FSMs have an output, output something, but not all of them do. So we'll see an example where we do have some output, but at first we're going to just start talking about a finite state machine that doesn't have an output. It just has a set of states, a current state, set of possible inputs, and then a set of rules to determine how the state of the machine will be affected by the various inputs. Let's first start with an example where we're going to look at a turnstile. So we're going to look at a turnstile, kind of remember how it works, and then see if we can come up with a finite state machine that will describe, that will show how a turnstile actually works. So I found this picture of a turnstile online, and actually I have the URL right here. That's actually a link to where you can buy this turnstile. So if you want to buy a turnstile, you can find it there at that URL. Anyway, this is an example of a good picture of a turnstile. Remember what this is, what happens with a turnstile. They usually have them when you're going into a building or going into an area where maybe you have to pay, have a ticket to get in. And so this turnstile will be locked and if somebody tries to push and go through, it could be locked. But then if the person has a ticket or pays a certain amount of money or something like that, then they will do that, and then they'll be able to go through, right? Now, there's some turnstiles that just turn all the time. You don't have to do anything. You can always push on it, and it push, and you can walk on through. That's when, like, maybe they're just trying to slow people down, or maybe they just want to count how many people are coming in. So it's true that not all turnstiles actually lock, but this example of a turnstile, we're going to pretend like it starts out locked, and then the person coming up to it would have to put in some kind of coin, money, some certain amount of money or some certain coin in order to be able to pass through. Okay, so that's the example. That's the type of turnstile that we're going to talk about right now. So let's pretend we have that, and we're going to see if we can create a model that describes this behavior. Well, okay, so a turnstile has, if we want to create a finite state machine, we need to come up with a set of states. Well, it can be either locked or unlocked, right? Okay, a current state. Well, that would be one of the above, depending upon whichever it is at any given moment, right? A set of possible inputs. Now, we're going to make this simple and just say that in order for a person to get through, they're going to insert some type of coin. And we're going to, not say to make it more complicated, although we will get to something a little bit more complicated later. But for now, we're not going to say, well, they have to put in, 2 quarters, or they have to put in, a certain amount of money. We're just going to say they insert a coin. So maybe just kind of pretend like that coin is some kind of token, and they have this one kind of token, and either they can use that token to put in, or they can't. But it's not like you can put in different amounts of money in this example. Okay, so the possible inputs to this actual device would be, well, we could put that coin in, or an input's not necessarily something that you're putting into a device, but it's something that you're doing to it. So the other one could be you're pushing on the bar so that you can walk through. Okay, so push and walk. Okay, so those are the 2 possible inputs, either put in a coin or push through. Okay, now there has to be a set of rules that's going to determine how this machine is affected by the inputs. Okay, so let's think about this here. For this particular example, a locked turnstile will change to unlocked as soon as that coin is put in, right? And here it says once the correct amount of money has been inserted. And remember that we're just staying real simple and just saying there's just going to be some coin that gets entered. So once this coin is entered, then a locked turnstile will change to an unlocked state. Now, an unlocked turnstile, think about what happens when you have an unlocked turnstile. What's going to happen? Well, somebody can walk through it, right? It's going to wait there until somebody walks through. So an unlocked turnstile is going to change back to a locked state after someone pushes it to enter. Okay, so those are kind of some rules on how do these, what has to happen, what kind of inputs happen in order to change the states. So that's those set of rules. Okay, now for this turnstile, this type of turnstile, there's not going to be any output. Nothing comes out of it. So we would say there's no output for that. So this would be a fairly simple model that describes our turnstile, although we really haven't gotten specific yet and laid out that set of rules. So in order to really define this finite state machine, we would need to set out very clearly the set of rules. And so we'll kind of be doing that here right now. So, but before we do that, let's go ahead and talk about some notation. So usually when we're talking about finite state machines, we denote states as, with certain letters and notation, and also the inputs and also the set of rules. So I just wanted to go through that and show you what those are. So the set of states, again, for turnstile, it would be locked and unlocked. we're going to call that set, the different possible states for a given model, we're going to call that Q. Okay, Q represents a set of states. So for the turnstile, we'd say it's locked and unlocked. Those are the two elements inside Q. And often we'll label the individual states with subscripts on the small letter Q. So we'll have Q naught, that 0, Q sub 0, we usually call Q naught. So I'll call it Q naught. So we've got Q naught, Q1, Q2, etc. So there's some other designations, but that's really often you'll see states designated with Qs. Okay, a current state, that again would be anything that it is at the moment. So if you have states that are Q naught, Q1, Q2, then the current state could be any of those, right? For the turnstile, it could be locked or unlocked. And we always have what we call a start state. How does this model, what's this, what are we assuming the very first state is when things just get started? What's the very first state? And we'll usually call that Q naught, Q sub 0. Okay, now a set of inputs, we call that the set I. So an example for the turnstile would be the set called I, and the elements are a coin is inserted and then push. Those are the two types of things that can be done to that machine. So those are the inputs. Okay, now we get to the set of rules to determine how the state of the machine will be affected by these various inputs. We use this, it's a function, it's always going to be a function, and we call it a transition function because we're talking about how the states of the machine changes. How does the machine go from one state to another? So that's why we call it a transition function, and we designate it just like we used I and Q above. We're going to designate our transition function by delta. And so that Greek letter delta is what we use. So you'll see, when you see that, you'll realize, oh, we're talking about a transition function. So we use that to represent those rules. Okay, so now what's that function going to look like? Remember what a function is. It takes something in and then spits something out, right? So what do we send into the function? We're going to send in the input, some input at any given time, and what is the current state before we put in that input. So that's what the function is going to take in, input and a current state, and then what comes out of the function will be a new state. Usually it's as simple as that. Sometimes the output of the function will include some other things. But anyway, that's what we'll use for those set of rules. We'll use delta, a function called delta for that. Okay, and if there is, okay, so here's an example for our turnstile. Let's see if this makes sense. This would just be one little part of this delta function for the turnstile. This says that if we put in send the input. The input would be the coin. Now this is in a different order, and then I say it takes an input and a current state. But then here, the first one, we put the state first and then the input. I think maybe I took this out of the book and that's how they did it. It doesn't really matter, obviously, right? If we know if it's for sure which is the input and which is the state, then it doesn't matter which order we put them in. So we're saying, what if the turnstile is locked and we do some input by inserting a coin? Then the result would be, that's the new state, it says here. So what would the new state be? Well, if we put a coin in, and we're assuming it's the right coin, then that state's going to turn to unlocked because the person's going to be able to go through. Okay, so this would make sense. If we pass in the input of coin into the current state of locked, we see that, yeah, it makes sense that the new state then would be unlocked. Now, in order to make a full transition function, we would need to show all of those possible combinations. But this is just an example here about what we call them, what type of notation we use. So we'll get into the more specifics on this here in just a minute. And then there's output. Sometimes we do have output. This turnstile doesn't have any kind of output. But if we had, like, let's say we had a vending machine, then the output might be like, the different items that could come out of that. So we could have some output there. So continuing with our example for the turnstile, we've already done some of this. Set of states, we would say it's locked and unlocked. Current state, let's say that it starts out as locked. And now the set of possible inputs, we've said that you can either put in a coin or you can push it. Then the set of rules, we've talked about that would be called the transition function, and we have to figure out a way to represent that. We're going to see 3 different ways to represent a transition function for this example. First of all, there is a way that we can do it, which is by creating a diagram. So we start with both of the states here. We can have locked or unlocked, so we're going to put a circle with each state there. Now, it might be that there are other states in another example, but in this case here, there's only 2. So we'll put locked and unlocked. We're going to put some kind of little arrow to show which we start in. So locked would be our start state. So we're going to start with locked. Then we're going to start needing to represent what happens when we put in some input. So here's what we would do. We would put this little arrow up there and representing what happens when we put in a coin. So we've said that if you put in a coin, the turnstile becomes unlocked, and then later you can go on through. So we'll have an arrow from locked to unlocked with coin up here saying that if I put in a coin, when the turnstile is locked, then the new state is going to be unlocked. Remember, this transition function, it's going to always take an input and then a current state, and then it's going to result in another state. And maybe it's a new state, maybe it's a completely different state, maybe it's going to stay the same state. It's some state. That new state might be new, might be the same one, but it depends on what's going on. So here in this case though, put in a coin, it becomes unlocked. Now, what if we push it when it's unlocked? Then the person's going to go on through, and then it's going to be locked again. So that's what happens when we go from, how we go from unlocked to locked. We would have to push on through. Now, there's a couple of other possibilities though. What about if it's locked and we try to push on it? Well, if we haven't put a coin in yet, then we're not going to be able to walk on through. We can try to push, but it's not going to move, right? So if it starts out locked and we push it, it stays locked. So we're going to have this little arrow here that turns back around like this and points back to the locked one. Here on the right, what if it's unlocked and somebody tries to put another coin in? Well, we're just going to say in this example that it's not going to give a message to the user or anything, and it's not going to return the coin. In this example that the book used, they decided they were going to assume that this particular turnstile is just going to always accept a new coin, even though it's already unlocked. So that would be shown here, that if it's unlocked and a person puts in a coin, then that's fine. It'll take a new coin, but it doesn't change. It's still unlocked, waiting for the person to push through. Okay, so that is an example. One way that we can one way that we can show this transition function is a diagram. But here's another way. Just look at all the possibilities and then say what happens. So for every set of possible input along with the possible state, then decide what's going to happen. So I'm just going to take one of these to look at. Let's look at the second one here. We're using delta because it's the transition function. The two things that are going to go into the function are, we're going to have a current state and an input. So we're going to say the current state is unlocked, but we try to push it. Okay? Well, we know that if we push on an unlocked turnstile, we'll get to go on through, and then what's the new state? It becomes locked now because it's ready for somebody else to put in the coin. So that makes sense. So you would just think through all these possibilities and decide what would happen. So hopefully you can look through that yourself and realize all of these really correlate to all of these different things over here in the diagram. You can also have a little chart like this where you have the states on the left and the inputs over on the top. And so, like for instance, if it's locked and you put in a coin, so if it's locked over here and you put in a coin, then you would look to see what's in that little box, and that would be the new state. So that's just another way that we can represent that same situation. Now we're going to look at a gumball machine and see if we can come up with a finite state machine that would represent what's happening with this gumball machine. Now, here you see a picture over here of this gumball machine. If you remember what happens when you're trying to use one of these, you put in a coin or more than one coin, and then you have to go one step further by twisting that little knob. So, but there might be some that instead of a knob, it has a button and you push the button. So different things like that. But you put the money in, and then you do some kind of action that says you're ready to buy that gumball, right? So anyway, just to keep that in mind here, let's start out by filling this out for this gumball machine. Now, what they're doing in their example is they're pretending like the gumballs cost 20 cents. And so what they're saying is that somebody can put in a nickel or a dime, and then until it comes to 20, and then once it gets high enough to 20, then they'll be able to get a gumball. Okay, so the different states for this gumball machine would be these different Q values, where the subscript represents how much money is in there. So we have Q naught, meaning there's no money in there, 5 cents, 10 cents, 15, 20, because those are the possibilities for putting in either nickels or dimes. Now it's going to start over each time a person gets a gumball. So that's why it doesn't keep going. It's not adding up all the money that's actually in that machine. It's just how much money has this current customer put in. Okay, so it goes from 0 up to 20. Now, and what we're doing in this example here is to keep things simple. We're going to pretend like that machine doesn't give change. So if you've already put in 15 cents and then insert a dime in there, then that's too much money. It's not going to keep 5 cents and give you 5 cents back. So it's not going to be that smart. It's just going to, we're just assuming with this example that it's just going to return the dime. If you give it too much, it returns returns that coin, and you have to just and it will still stay the same where you don't get your gumball yet, but you would have to put correct change in there, the exact correct change, in order for to be able to get the actual, make the purchase. Okay. Now the current state, well, it depends on when we're asking, but at the very beginning we're going to say that the current state is Q naught because no money has been inserted. Set of possible inputs, we're saying that you can either put in a nickel or put in a dime, or you can twist that little knob. So that's what we're going to represent by the word buy. Either twist the knob or push the button. Maybe there's a button that says buy or something, but we're going to represent that little extra little thing you have to do when you think you have the right money in there that will then make this gumball come out. Okay, now how are we going to represent these rules? Well, probably because this is a little bit more involved than that last one, the easiest way, believe it or not, would be using a diagram because there are so many different possibilities. So here's what a diagram would look like. And as you can see, it is a lot more involved. And we'll talk about that here in a minute. But I do want to say this too. This particular finite state machine does have an output, right? Because either, no matter, depending upon what happens, we might get a gumball back, or some money, like our dime, might be returned. Our last coin might be returned. I hadn't said this yet, but they're setting it up to say that you'll get a message if you try to buy something and you haven't put enough money in yet. So if you only put in 15 cents and then turn that little knob, you would get a message saying, you need to put some more money in. And then there's also a possibility that nothing happens. If you just put in a nickel, nothing's going to happen. It's waiting for more money. Okay, so those are the outputs. So the reason why this diagram looks kind of more involved is because there's not only the inputs in blue that it's showing here, but there's also in green, it's going to be showing the output. Okay, so let's start with Q naught, which would be the start state where no money has been put in yet for this current customer. And let's say they put in a dime. Okay, if they put in a dime, then this, I'm trying to get the that to work here. So we're going to go along this red one here, this red arrow where we put in a dime. What's the output there? Well, this says none, and that's true. Nothing would happen yet. It's waiting for more money. If I put in another dime, I get over to here, and I didn't show this, but the first time we put in a dime, we got to Q10. Second time we put in a dime, we're at Q20. Again, no output yet until we try to turn the dial or do that buy action, whatever it is. If we do that, then this is what happens here. We follow along this way. We're going to push the buy button or turn the buy handle, and we'll get some output. We'll get the gumball, and then the state will now be Q naught again. So that's an example of what would happen if you put in just 2 dimes. Maybe you would want to put in, another combination. So let's say I'm going to try a few different things here. Let's put in a nickel. So we start right there, put in a nickel, and then let's say we try to buy it right then. So we put in a nickel, then we're going to go around here, and it's saying that it's going to stay in the same state. It's not going to change because, by turning the handle, if we only have 5 cents in there, it's not going to change the state and give us more money. So it's going to stay in that state, and you would get a message saying you got to keep putting more money in. So then maybe we'd put a dime in next. Then we would get to here. So we would get to Q15. What if we're at Q15 and we put in a dime like that, like we mentioned that earlier? We said if we have 15 cents and we try to put in a dime, we said that it should just return the dime. So here we go. Here's this one here. Right here, that little area right there. It's going to, the top one, it says the input is dime, and it's just going to return that dime. Okay, or if we don't put in a dime, but we try to press the buy button or turn the buy handle, we'll get a message. So hopefully you can look at all those possibilities, and hopefully it makes sense that diagram does represent this particular gumball machine. We have one more example, and in this example we're going to show how we can use a finite state machine to represent some process where we're recognizing certain properties. So in this case here, we're talking about an input string, so pretend like maybe somebody's typed something into a computer. And what we want to do is say that in this example here, we're going to say that we want to check and see if that password that the person typed in starts with a letter here, it says, and contains at least 1 digit. starts with a letter and contains at least one digit. So this here turns out to be the diagram for this situation. So we'll talk it through so that you can understand, see how this makes sense. I do want to say something up here that I didn't talk about yet. And in a situation like this where we're trying to recognize if a certain property has been, is upheld, then we're going to have some states that we consider what are called accepting states. So in this example here, if we find that input value that the person typed in does start with a letter and contains at least one digit, then we would want it to end up at at one of its states to be what we call the accepting state, the state that says yes, everything's good. Right? And then there would be the other states would mean, if we end up with another state and never can get to that accepting state, then we would be saying that property that we're looking for, it is not fulfilled. Okay, so anyway, let's look through this and see if we can figure out and see if this makes sense how we would do this. I'm going to say, let's say that I start out by putting in this password, 3AB. So we know that's not right because it says it has to start with a letter. So let's see what would happen with this diagram. So we're going to start at the start state right here. And the D stands for the fact that we are inputting a digit, and L stands for inputting a letter. So this first one here that I input here for this password was a 3. So that means we're inputting a digit. So we're going to go this way here, and that's going to take us to an invalid state. And no matter what I do afterwards, here I can put in a digit or a letter. No matter what I do for as many times as I want to, I'm only going to stay in this invalid state. So we see that is not going to work, and I do not get a valid password that way. But let's say I put AB3. Then let's see what happens there. Let me see if I can erase this here. Okay, so with AB3, I start out here, I put in a letter. Now, that's not accepted as a great password yet because it's still waiting to find out if I'm going to put a digit in, because remember, we have to have at least one digit. So it's going to stay at undecided. Then I put in a B, so that's another letter. It stays at undecided, still not sure. But as soon as I put that digit in, that's what it's waiting for. I put in a digit, that takes me to the valid state. So, and then that is the accepting state. And notice I could put other stuff here after it. I could put more digits and more letters, and it would just be going around here, around here, around here, and continuing to stay in the valid state. Okay, so that's a nice little example of a finite state machine that will go through this process of determining if something, validating something, determine if a property holds up or not.